This video is part 2 of my kinetics videos. Part 1 we talked about the basics of rate equations, getting rates from concentration time graphs and the initial rates method. Part 2, which is this video, is about working out orders and an example of this, the shapes of the rate concentration graphs for the different orders and the overall order of reaction. Part 3, which will be the next video, will be all about the rate constant K, finding out the units of K for different situations, calculating the value of K, how temperature affects K, and the Arrhenius equation. Let's start with orders. So orders are pretty easy to understand when you know what you're looking for. So you'll have rate equals K times a reactant, say reactant 1, with an order of X, and reactant 2 with, say, an order of Y. Now we don't know what X and Y are, but what you can do is just use simple maths to figure out what they are. So when something is zero order, it basically means there is no change. When the concentration increases, there's no change on the rate, it stays the same. When it's first order, when the concentration of something increases, say doubles, then the rate also doubles. The rate increases by the same factor. Now when we have second order, when the concentration increases, the rate increases by the squared factor of that. So if the reactant, so the second reactant, if Y was 2, was doubled, the rate would actually quadruple 2 squared. So it's quite simple to understand when we put it like this. So if the concentration, so square brackets, if you remember, stands for concentration of something. So if the concentration doubles and the rate stays constant, that means it's zero order with respect to whichever reactant you're looking at. If the concentration triples and the rate stays constant, it's also zero order. That's because any number, say x to the power of 0, is 1. So it'd be rate equals, if we ignored R2 for the minute now and we just looked at R1, pretend R2 didn't exist, any number there, could be a million, could be 5, could be 0.5 to the power of 0 equals 1. So rate will just equal K. It will stay constant no matter if the concentration goes from 5 to 10, that bit there will always equal 1, so rate will always equal K. Now if we look at the concentration, if that doubles and the rate also doubles, that indicates it's first order. If the concentration triples and the rate triples, this also indicates first order. This is because if the concentration is doubled and it's first order, it's like 2 to the power of 1. 2 to the power of 1 is just 2. Because that stays as 2, that also means the rate doubles. If that value was 1 originally, we'd have rate equals K. So rate equals K times 1. Now if we doubled R1, we'd now have rate equals K times 2, therefore the rate has doubled. Now if we look at the concentration, if the concentration doubles and the rate quadruples, this indicates it's second order. That's because when you double it and it's second order, it's equivalent of 2 squared, which is 4. And if we look here, if the concentration times by 3 and the rate increases by 9, then that's also second order, because we've increased the concentration by 3, but because it's squared, it's made 9. So we can always do something, say the number 3 to the power of x equals 9, and if that was 2, x would have to equal 2, meaning it's second order. If we had an equation 3 to the power of x equals 3, so that's like this example here, then, well, x would have to equal 1 to make 3, and for this example just here, we would have 3 to the power of x equals 1. Well, to get 3 to equal 1, x would have to equal 0. So you would have 3 squared equals 9, 3 to the power 1 equals 3, and 3 to the power of 0 equals 1. When you know what you're looking for, it's quite straightforward, because if the rate stays constant even though the concentration is changing, it's zero order. If the rate is increasing by the same amount as you're increasing the concentration, it's first order. And if the rate is squared what you're changing the concentration by, it's second order. let's look at an example of this. So we have a reaction here. 2 lots of H2 plus 2 lots of NO goes to 2 H2O and N2 in the gaseous state, and this will be done at quite a high temperature. If we look at we've got the rate here, we've got the concentrations of each reactant. Now this is the first rate. We've got 1 mole of hydrogen, 1 mole of nitrous oxide, and the rate is 1 times 10 to the power of 3 moles per dm cubed seconds to the minus 1. Now if we take H2, well actually first of all let's look at the rate equation. So we've got rate equals K, there's always a K, times by concentration of H2 to, let's say, the power of X. That could be 0, 1 or 2. And times by the concentration of NO to the power of Y. That could also be 0, 1 or 2. So we look at hydrogen first. Well, in the first reaction between these two, NO stays the same. So we can kind of disregard this bit because it stays the same. It's not going to affect the change in rate. This change between these two are coming about because of the change in hydrogen here. So we look at the change in hydrogen. The concentration of hydrogen is doubled and the rate also doubles. Well, because of that we look, okay, concentration times 2, rate times 2. Well, the rate is increased by the same amount as the concentration is increased by. So that would indicate that it's first order. Because if we remember, first order is an increase of rate by the same amount you increase concentration. Second order would be the concentration squared, and zero order would just be no change at all in the rate. So that indicates it's first order with respect to hydrogen, and therefore X equals 1. Now if we do the same but for nitrous oxide, we want to look when hydrogen's kept the same. Okay, so the concentration of hydrogen is kept the same between 1 and 3, if we label 1, 2 and 3, between 1, 2 and 3. The rate between 1 and 3 is increased 9-fold, interesting. Now we look between 1 and 3 of nitrous oxide, we can see there's been an increase of times 3, and here there's been an increase of rate of times 9. So the concentration has increased by 3, and the rate has increased by 9. What does that indicate? Well, 3 squared is 9, therefore that indicates that it's second order with respect to NO. And that leads us to say that Y equals 2 when you look at the rate equation earlier. That means the overall rate equation will be rate equals K, the constant that's in every equation, times by H2, which is to the power of 1, so we can just omit that. Anything to the power of 1, it's just itself, times by nitrous oxide to the power of 2 as its second order. So that would be our rate equation for this example here. Now let's look at the graphs of different orders. So this is a rate versus the concentration of reactant. Now this graph here is 0 order. This graph here is first order, and the last graph on the end is second order. Now these are something that you can choose to memorize, and that's something, if you memorize it, then that's brilliant, you don't have to learn why, but I'm going to take you through the shapes of these graphs. Well, here we've got a constant ratio, so if you remember, rate equals K times by a reactant to the power of X, so it could be 0, 1 or 2, or it could be higher, but in terms of A level you won't go above 2. So if we've got something that's changing on the x-axis but staying the same on the y, well that would be a y equals m. If you remember the general equation for straight lines is y equals, well, a function mx plus c. Well, y equals c, I should say in this case, y equals c, as it's just a constant value. Well, how do we get that? Well, if it's 0 order, that becomes 0. Therefore, that term there, reacted to the power of x, all becomes a value of 1. So rate equals K, rate equals K. Well, as you can see, rate is the same as Y equals the same as equals, and K is the same as C. So we see here, when rate equals K, because anything to the power of 0 is 1, we get a straight line like this. So that makes sense. When you use simple maths, you can see that a zero order graph of rate versus reactant concentration is just a straight line. Now if you look at the same thing but for first order, well, we get a straight line like this. That's because when x equals 1, it's just the same as the concentration of reactant. So now we've got rate equals K times the concentration of the reactant. Now that's a bit like a y equals mx graph, isn't it? An m times x. Because this is the x value as reactant, so that's the x value, and it's time, so it's a bit like a gradient. Well, we just have a straight line gradient here. So simple as y equals mx. Well, you could have the plus c, but in this case the plus c is just 0, so y equals mx plus c, where c is 0, is just y equals mx. And that's how we get the shape of the first order graph. If we look at second order graph, you've got squared, so rate equals K times by the reactant concentration squared, which is a bit like y equals mx squared. And if you've done maths, you'll know what the function of sort of x squared would kind of be like a bowl type shape is a good way to describe it. And that's how we get the shape like that. And again, it crosses the axis at the bottom, so the plus c would just be a 0. So y equals mx squared, that's how we get that shape, the second order. Like I said, you can just memorize this if you want, but here is I've just shown you how you actually get those shapes of graphs just using this rate equation here. So when x equals 0, that term effectively just turns to 1. When it equals 1, it's just itself, and when it equals 2, it's squared. So we get y equals c, y equals mx, and y equals mx squared. Now let's look at some different types of graphs. So again, you can just remember these, and to be honest, I would say they're easier to remember than actually look at the maths behind it. So this is a concentration of reactant on the y-axis against time. So here we have zero order again. We have first order for this graph and second order for this graph. Well, this is just a straight line. As you can see, we've got a straight line and two curves. It's nice and easy just to point out zero order, just a straight line. As the rate of reaction remains constant throughout. It never changes. You could increase the concentration by loads, but the rate stays the same. Get this nice straight line. This one here, you have a half-life, symbolized by t a half, is constant throughout. How you figure that out is if you have a concentration, say it started at 1.00 moles per dm cubed, and it went down to 0.50 after, say, 50 seconds, it would take to get to there, then a constant half-life means basically the concentration halves at the same time interval. So every 50 seconds, concentration will halve. So to get from here to here, it will take another 50 seconds, and so on. So you go to 0.125 moles, it will take another 50 seconds. And it comes out with a curve kind of like that, because the concentration is dropping by half each time for the same time. Now, an easy way to remember the second order graph is just purely to go, it's the odd one out. It's like no explanation. You've got straight line is zero order, constant half-life is first order, second order is just the odd one out. It may look like this, it can look different, it can look a little bit different. Basically, it just doesn't have it's a curved graph that doesn't have a constant half-life. So the overall order of reaction is the next thing. Well, if we go back to the earlier example where we have rate equals K H2 and NO squared, well, we see that it's first order with respect to hydrogen, second order with respect to nitrogen monoxide. That's equivalent of writing H2 first order and NO second order. Now how you get the overall order is just simply to add those. So it's the first order plus the second order reaction, which is a total of third order overall. And it's nice and simple. You can just simply add them together. There could be another reactant in there. For example, we could have another reaction where you got reactant 1 to the power of 1, reactant 2 to the power of 2, just like this, and that would be third order overall. We could still also have third order overall if we had reactant 3 to the power of 0. Anything to the power of 0 is 1, so we wouldn't actually write it in the equation. We would just have those two there, but there could be something else that would be involved, but because it's 0 order, there's still a third order overall. That's the end of this video. Please like, share and subscribe. Part 3 will be on its way shortly. If there was anything you didn't understand the basics rates, have a look at part 1 of the videos where I just go over like what the rate constant is and things like that. Please look at part 3 if you're interested in the rate constant K and the Arrhenius equation. Please share this with your friends, like and subscribe. Thank you.